Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Thin Film Deposition Techniques from the paper Nanoscience and Nanotechnology. So students, let us see what we are going to learn in this module. In this module, the principle and working of vacuum deposition techniques is described. Then, various physical vapor deposition techniques such as iron plating, iron implantation, sputtering, and surface alloying are discussed in details. The principle and the experimental setup of chemical vapor deposition method is studied in this module. Finally, advantages, limitations, and applications of various thin film deposition techniques are discussed in this module. Thin films of various materials have been the focus of much research owing to the vast applications in electronic and optoelectronic devices. These applications stem from the ability to deposit stable thin films of controlled morphology and thickness. The traditional processes to produce thin films involving casting and spin coating do not meet the requirements of advanced device technologies. With advanced industrial requirements, uniform and stable nanometer thick films are needed. Additionally, many functional materials are not soluble in the common solvents. In such cases, vapor deposition techniques can be promising candidates to fabricate advanced functional devices. Let us discuss about the vacuum deposition technique. Vacuum deposition is a group of various deposition techniques which are employed to deposit thin films or layers of a material onto a substrate by atom or molecule by molecule manner. The processing is carried out at pressures lower than the ambient temperature, that is, in vacuum. The thickness of the deposited films varies from atomically thin to a few millimeters. This technique can also be used to produce freestanding films of a material. Consequently, alternate layers of different materials can also be deposited using this technique. As an example, this technique can be used to produce optical coatings where layers of different materials are present on top of each other. Figure 1 shows the operating principle of vacuum deposition, where we have a substrate onto which the thin film is deposited. The source material, which is to be deposited, is kept in an evaporator and is connected to a heater. The entire thing is placed in a vacuum chamber. When the source material is evaporated, it gets into the vaporized phase and then condenses onto the substrate to form a thin film. The purposes for depositing films under vacuum are: first, the particle density is greatly reduced. Therefore, the mean free path during collisions is long. Secondly, there is less contamination. Then, there is low pressure plasma conditions. Also, the composition of the gas and vapor can be easily controlled. Then the flow of the vapors can also be controlled. The condensing or depositing vapors can be produced by thermal evaporation, sputtering, arc vaporization, etc. In reactive deposition, where certain chemical reactions occur during the deposition process, the following reactions can take place. First, the depositing species may react with a component of the gases present in the reactor. Example, titanium plus nitrogen on chemical reaction will give titanium nitride. The depositing species may react with the co-depositing species, that is titanium plus carbon leads to titanium carbide. The plasma environment activates the gases, that is N2 it converts to 2-nitrogen and decomposes the precursor vapors, that is SiH4 into silicon plus 4 hydrogen. The other uses of plasma include precursors can be vaporized by sputtering. The substrate can be cleaned by ion sputtering. To densify the structure and control properties, such as ion plating. Let us discuss about the classification of vapor deposition processes. On the basis of the type of vapor source which is employed in film deposition, these processes can be classified in the following two categories. First one is the physical vapor deposition. This technique uses a solid or liquid vapor source. Second one is the chemical vapor deposition. This technique uses a chemical vapor. Vapor deposition processing includes techniques which deposit materials in a vapor state by condensation process, chemical reactions, or certain type of conversion processes. The deposition process is known as physical vapor deposition if a liquid or solid source is used to create the vapor phase. However, if vapors are produced by chemical reaction, the process is chemical vapor deposition, that is CVD. Generally, a combination of both these techniques is used. Let us now discuss the applications of vacuum deposition techniques. Vacuum deposition techniques find diverse range of applications such as electrical, semiconducting, as well as insulating coatings. Then they are very useful in optical coatings. They serve as good materials for reflective coatings. They are perfect film lubricants. Also, they have low emissivity, which is useful in glass coatings and smart film coatings. They can be used as diffusion barrier coatings, etc. The next deposition method, which is the physical vapor deposition method. Physical vapor deposition includes a group of vacuum deposition techniques which are employed to synthesize thin films as well as coatings. In PVD, the material goes from a condensed phase as precursor to a vapor phase and then back to the condensed phase, which is deposited as thin films. Commonly used PVD techniques include sputtering, laser surface alloying, iron plating, and iron implantation. It is widely employed to produce thin films for mechanical, optical, chemical, or electronic functions such as semiconductor devices including thin film solar panels, aluminized PET film for food packaging, and balloons and coated cutting tools for metal working, etc. The most frequent coatings developed by this technique are titanium nitride, zirconium nitride, chromium nitride, titanium aluminum nitride. In physical vapor deposition technique, the film is deposited over the entire exposed area of the object. It is basically a vaporization coating method involving atomic scale transport of the material to be coated. The gas phase precursor condenses onto the substrate, thereby creating the required layer. No chemical reactions occur during the deposition process. The process is performed under vacuum and it comprises the various steps which are explained. Now discussing the various steps in the physical vapor deposition route, the first and foremost is the evaporation. We can see in the flow chart, the first one is the evaporation. Target or the material to be coated or deposited is incident with high energy source like an electron or ion beam. The atoms from target surface are removed, thereby vaporizing them. Then next step is the transport. The atomic vapors, they are carried from the target surface to the surface of the substrate which is requiring the coating. The next step is the reaction. The step is introduced if the deposition is to be of compounds of target metal atoms such as metal oxides, nitrides, carbides, and the like materials. When the metal atoms of the target vaporize, they react with the gas intentionally introduced to react with target material during transport phase, thereby depositing products of these metal atoms. The last step is the deposition. It involves coating buildup on surface of the substrate. Based on specific method, certain reactions may take place between the target material and reactive gases on the surface of substrate concurrently along with the deposition process. Figure 2a shows the flow chart of the physical vapor deposition technique where we can see if the source is either in solid or liquid phase, evaporated to convert into gas phase, then in the gas phase they are transported and deposited onto the substrate to convert into solid phase. Let us now study the experimental setup of the physical vapor deposition technique. Figure shows the experimental setup which is used for the physical vapor deposition technique. The experiment is performed in a quartz or alumina ceramic tube. Depending on the application, the tube may be fitted either horizontally or vertically. Let us next discuss the ion plating technique, which is via plasma. Metals including titanium, aluminium, gold, copper, and palladium are deposited on the surface of a feature via plasma-based ion plating. The thicknesses of the deposited layers vary between 0.008 to 0.025 nanometer. The advantages of this technique are good adhesion, surface finish, in situ substrate cleansing before coating, and good control over the film geometry. However, its disadvantages include tight control of process parameters, plasma contamination, and possible contamination of substrate and deposited layer by the bombarded gas species. It is widely used in X-ray tubes, piping threads, turbine blades in aircraft engines, steel drilling bits, etc. Before performing experiment, reaction chamber is evacuated at the pressure 10 raised to a minus 4 to 10 raised to a minus 7 torr range. Then, heating element is turned on and with a constant flow rate, carrier gas is introduced into the chamber. Introduction of carrier gases increases pressure inside the chamber and it becomes 200 to 500 torr. Flow rate of carrier gas depends on structure of required nanomaterial because morphology of produced nanostructure greatly depends on pressure of chamber and flow rate of carrier gas. After achieving necessary conditions inside the chamber, gas flow and temperature of chamber are kept constant for deposition time. Precursor materials are vaporized at high temperature and low pressure conditions. These vapors are then transferred by inert gases to lower temperature zone where they progressively supersaturate. When they reach the substrate surface, nucleation and subsequent growth of desired nanostructures takes place. The growth can be terminated by turning off the furnace. The reaction setup is cooled to the surroundings by flowing inert gas through it. We next move on to study the sputtering process. Sputtering alters the physical properties of any surface by etching mechanism. A gas plasma is created between two electrodes. That is, the cathode, it comprises the material to be deposited, and there is an anode which acts as the substrate on which deposition is required. Typical depositions are thin films with thickness varying from 0.00005 0.00005 to 0.01 mm. Typical depositions are of chromium, titanium, aluminium, copper, molybdenum, tungsten, gold, and silver. Applications include decorative coatings like watch bands, eyeglasses, and jewelry. In comparison to other deposition techniques, sputtering is an economic and cost-effective process, and thus it is extensively used in numerous industries. It is widely used in electronics industry for producing heavily sputtered coatings and films. Such coatings include depositing thin film wires on chips, recording heads, magnetic and magneto-optic recording media, etc. Automotive industry uses sputtering to prepare decorative films for plastic. In buildings, it is used to create reflective films for large pieces of architectural glass. The food packaging industry uses sputtering to produce thin plastic films for packaging. Let us next discuss about the surface alloying technique. Surface alloying, or I can say modification, by using lasers facilitates alloy formation by introducing the selected material into the melt pool. This process produces surfaces exhibiting good performance at elevated temperatures, improved wear, and corrosion resistance, enhanced mechanical behaviors, and good appearance. Laser cladding is the most common process in surface alloying. Laser cladding is used for selective deposition over a specific area. In this technique, a thin metal layer is mixed with some base metal by combined application of pressure and heat. Elaborate sample preparation step is not required, yet the surface might require to be made rough before coating. Grinding and polishing are usually done after the deposition. However, readily oxidized materials require inert gas streams for deposition. Laser power, its frequency and speed affect the deposition rates. The thickness of the deposited layer varies between few hundred micrometers to millimeters. If the deposited layer is highly dense, film cracking may result in delamination. Furthermore, this technique only deposits in the line of sight. We will now study the chemical vapor deposition method, which is also abbreviated as CVD. CVD is the most extensively utilized technique to prepare good quality, extraordinary performance solid materials. Its most popular applications include producing thin film coatings on surfaces, but it can also be used to synthesize high quality powders and bulk materials. Composite materials can also be fabricated by the infiltration technique. CVD is also employed to deposit almost all the elements of the periodic table, sometimes in their pristine forms, but more often combined compounds. Conventionally, a precursor gas or gases is introduced inside a chamber, and closing the preheated substrates needs to be coated with. Chemical reactions take place on and near those heated substrates, leading to the deposition of thin films of desired material on surface of the substrate. The deposition is accompanied by production of byproducts which needs to be removed from the reaction chamber along with the non-utilized precursor gases. Figure 3 shows a conventional CVD experimental setup along with the schematic of the process. The steps involved can be described as follows. Firstly, the transport of the reactants in gas phase, usually with carrier gas, takes place to the reaction zone. Then, the diffusion or convection takes place through the boundary layer. Adsorption of precursors takes place on the substrate. This is followed by surface diffusion of the precursors to growth sites. Reactions without diffusion may lead to rough surface growth. Then, the surface chemical reaction, formation of a solid film, and formation of byproducts takes place. The next step is the desorption of byproducts. Finally, the removal of gaseous byproducts takes out of the reactor takes place. As can be anticipated, due to the multiplicity of the deposited materials and wide-ranging applications, several types of CVD have been developed. It can be carried out in hot or cold-walled reactors very low to above the atmospheric pressures in the presence or absence of carrier gases at typical temperatures varying from 200 to 1600 degrees centigrade. Some enhanced CVD processes involving the use of plasma, lasers, photons, hot filaments, ions or combustion reactions so as to boost the deposition rates and also to reduce the deposition temperature. There are several processes in this technique which include sputtering, ion plating, plasma enhanced CVD, low pressure CVD, laser enhanced CVD, active reaction evaporation, ion beam, laser evaporation, etc. All of them differ in the manner the chemical reactions are initiated and can be distinguished by their working pressure range as follows. First, ultra-high vacuum, which corresponds to the pressures less than 10 is to the power minus 6 Pascal or approximately 10 is to the power minus 8 torr. Then the low pressure, these techniques benefit from lesser gas phase reactions at low pressures, thereby improving the uniformity of the film. Last one is the atmospheric pressure. Let us next study about the ion implantation. Ion implantation does not create an overall new layer, but it forms alloys with the substrate surface, thereby altering the chemical composition of the surface. For instance, nitrogen is employed to enhance the wear resistance in metals. Substrate cleaning prior to the deposition process is highly critical in this technique, as it works on the species which are present on the surface of substrate. Therefore, it is highly prone to contamination-led problems. The process is carried out in room temperature and the time required for deposition depends on substrate temperature resistance and the desired coating material. Ion implantation chemistry is only limited by the number of elements which can be vaporized and ionized within a vacuum chamber. Advantages are reproducibility, no post-treatment, and low waste production. If the coating is exposed to elevated temperatures, it cannot produce good finish. Limitations of ion implantations include complications in quality control, insufficient know-how, and equipments. Typical applications of ion implantations include anti-wear coatings for high-value components in biomedical devices, then tools and gears and balls in aerospace industry. It is also used in semiconductor industry to deposit gold, ceramics, etc. onto a variety of substrates, example plastic, ceramic, silicon, gallium arsenide, etc. Pre-treatment of the substrate involves mechanical and chemical cleaning, vapor honing for improving film adhesion. Additionally, the reaction chamber must be clean, leakage proof, as well as free from dust and moisture. Chemical vapor deposition is employed for improving corrosion and wear resistance of the materials. Typical depositions include nickel, tungsten, chromium, and titanium carbide. CVD has numerous benefits as thin film deposition technique. The chief advantage is that the films grown by this method are conformal, which implies that the thickness of the film on side walls of the objects is similar to that on the top. Consequently, films are uniformly coated to highly bent pieces. Another advantage of CVD is that besides depositing a wide array of materials, it can deposit extremely high purity films. This is due to the comparative ease in removing impurities from the gaseous precursors via distillation techniques. Further advantages are fast deposition rates along with the fact that it does not involve as low a pressure as the PVD process. So students, let us now summarize what we have learned in this module. In this module, the principle and working of vacuum deposition techniques was described. Then, various physical vapor deposition techniques such as ion plating, ion implantation, sputtering, and surface alloying were discussed in detail. The principle and the experimental setup of chemical vapor deposition method was studied in this module. Advantages, limitations, and applications of various thin film deposition techniques were also discussed. Thank you students for your attention.